Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most puzzling yet beautiful ideas in all of physics, the question of whether time itself could ever freeze at the speed of light. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see how we gather from every corner of the earth, each of us wrapped in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Time, it slips, it stretches, it vanishes when you're happy and lingers endlessly when you're waiting in line. It can feel soft as a Sunday morning or heavy as a sleepless night, but could it ever stop entirely? Could time itself, the very thing that carries us forward, come to a standstill? That is the question we'll let float softly through our minds tonight. To begin, imagine you are standing by a quiet road at dusk. The sky has turned lavender and the air is cooling. You hear the faint hum of a car far away. At first the sound is soft, almost hidden in the background. Then steadily the car approaches, the sound swelling, and finally it passes in a rush of wind. For you, standing still, the car is fast. But for the driver inside, sipping coffee and fiddling with the radio, the speed doesn't feel remarkable. They are at rest in their own little world. This small example holds a whisper of something profound. Speed, after all, is always measured relative to something else. To you, the car was fast. To the driver, the world outside was rushing by. But what happens if we try to imagine something moving at the greatest speed the universe allows, the speed of light itself? Could there be an ultimate view, a final limit, where even time surrenders and stops flowing? Of course, that's not how the story starts. To reach that point, we have to take a gentle walk through the history of physics, not with chalkboards and strict equations, but with soft metaphors like stepping stones across a quiet stream. And each step will carry us closer to the edge of light and to the strange possibility of time freezing. Einstein once asked himself a curious question. He was just a young man then, still working in a patent office. He wondered, what would the world look like if I could chase after a beam of light? A simple daydream perhaps, but one that reshaped the universe. If you could keep up with light, what would you see? A frozen wave? A still glow? The thought was absurd and yet deeply revealing. It hinted that our everyday ideas of speed and time were far too small, too human. As we drift with this question, notice how it feels almost dreamlike. We are not straining to solve equations. Instead, we're letting images arise, a beam of light, endless and bright, rushing yet untouchable. If you could catch it, time for you would no longer tick the way it does now. Seconds would lose their rhythm, moments would collapse together. This is the seed of the idea we will explore tonight. Before we hurry forward, let's rest on a small but comforting thought. Even here, on Earth, time is not as rigid as it seems. Two clocks placed in different conditions will tick at slightly different rates. One perched high on a mountain ticks a little faster than one by the sea. A clock riding on a satellite above us drifts out of sync with a clock in your pocket. Engineers at NASA have to constantly adjust these differences so that your GPS can tell you where you are, whether you're walking down a busy street or waiting for a bus. It's a small detail, almost invisible, but it reminds us. Time already bends and flexes in the everyday world. It's not frozen, but neither is it absolute. And so, when we whisper the question, could time freeze at light speed? We're not stepping into pure fantasy. We're leaning into the real mysteries that physics has already uncovered. The path ahead will bring us to astronauts aging differently from those they left behind, to invisible particles living longer because they move so quickly, to black holes where time seems to stretch almost endlessly. And if we follow that thread far enough, it will take us to light itself, where time, in some sense, vanishes. But for now, just breathe with this image. You sitting here wrapped in the quiet of your room, while outside light from distant stars has been racing across the universe for billions of years. Those photons, those tiny travellers, have no clocks of their own. For them, there is no waiting, no growing older, no before or after. There is only the journey and the moment of arrival. What does it mean then to ask whether time could ever freeze? Perhaps it is less about a literal stopping of seconds and more about stepping into a perspective where seconds themselves lose meaning. Like standing in the middle of a dream where you don't know if it lasted for hours or only a breath. Our exploration will move slowly, gently. We will not try to race toward the answer. Instead, we will drift, the way light itself drifts through space. From here, the story opens into the foundations of relativity, the strange rules of speed and time, and the quiet evidence scattered across the cosmos that shows us just how elastic time can be. So let your body relax, let your thoughts soften. You're safe, you're held by gravity against the earth, and yet your mind is free to wander. The night stretches ahead, and our quiet question, could time freeze at light speed, waits patiently, like a candle flickering in the dark. If we follow the thread a little further, we begin to see how our everyday understanding of speed is only the faintest hint of a much deeper story. You and I measure speed all the time without thinking. A jog in the park, a train sliding into the station, the way the hands of the clock seem to hurry on a Monday morning. Speed, to us, is simply distance over time. But this simple idea hides something astonishing. The closer you move to the ultimate speed limit, the speed of light, the stranger time itself becomes. Imagine for a moment a train pulling out of a station. Inside, children are playing, people are reading newspapers, someone is sipping tea. If you stand on the platform and look through the windows, you see them moving along with the train. But to them, it feels like nothing unusual is happening. Their tea isn't sloshing oddly, their newspapers aren't blurring. From their perspective, they are still. Now imagine another observer, perhaps on a different train moving in the opposite direction. To them, the first train seems to be moving twice as fast. To each person, reality looks a little different. This relativity of motion is ordinary, part of daily life. But in the early 20th century, scientists realized that when we push this idea to extremes, something radical happens. It is not only space, the measure of how far and how fast, that changes. Time itself bends along with it. Albert Einstein proposed that the universe has a kind of cosmic rulebook. In it is written one unbreakable law. Nothing with mass can move faster than light. Light, unlike every other traveller, keeps the same pace for everyone, no matter how you chase or flee from it. If you sprint toward a beam of light, it will not appear to you as moving faster. If you run away from it, it will not slow down. Its speed is fixed, steady, unchanging, a constant drumbeat of the universe. This leads to a subtle but beautiful shift. Since light refuses to bend its pace, something else must give way. And what gives way is time. The faster you move compared to someone else, the more your seconds and minutes stretch out compared to theirs. This is called time dilation, but don't let the technical term weigh too heavily. Think of it instead as time turning into soft dough, stretching thinner as you move faster. To make this less abstract, let's return to Earth. Orbiting above us right now are satellites, spinning silently in the sky. Many of them are part of the global positioning system, the GPS you use on your phone to find a cafe or navigate through city streets. Each of these satellites carries precise atomic clocks. And here's the curious part. Without constant adjustment, their time would drift away from ours on the ground. Not by hours, not even by minutes, but by tiny fractions of a second each day. Yet those tiny slips would add up to errors of several kilometers in your location. Imagine ordering a taxi and watching it arrive in the wrong neighborhood because relativity was ignored. The reason for this drift is twofold. The satellites are moving quickly, so their time slows down ever so slightly compared to ours. At the same time, they are further from Earth's gravity, which makes their time tick a little faster. Both effects, motion and gravity, must be accounted for, or else the system would unravel. In other words, your phone's blue dot is proof that Einstein was right. Think of the wonder in that. A quiet idea born in a patent office over a century ago now guides hikers in the mountains, pilots in the sky, and drivers in cities. The flow of time, once thought to be absolute and universal, turns out to be flexible and personal, shaped by speed and by the pull of gravity. And this flexibility is not just a theoretical quirk. Physicists have measured it in laboratories, in satellites, in particles from space. The faster you move, the slower your clock ticks compared to someone who stays behind. This does not mean you feel anything unusual while you're moving. To you, inside your train, your car, or your spaceship, your heart still beats the same, your tea still steams at the same pace. But to the observer who stays behind, your seconds lengthen. It is as though time is loyal to each traveller. It flows faithfully for you, no matter how fast you go. But from the outside, its pace changes. That is the gentle paradox at the heart of relativity. Time is both personal and relative, intimate and elastic. You might wonder if this is just a trick of measurement, like a faulty clock. But the experiments tell us otherwise. Particles created in the upper atmosphere, known as muons, should vanish in a blink. Yet when they are moving close to the speed of light, they last long enough to reach Earth's surface, defying what we would expect if time were the same for all. The only explanation is that their time is genuinely stretched. So we arrive at a gentle but profound realization. Speed does not only carry you through space, it bends your passage through time. The faster you go, the more your journey is drawn out, not in space, but in seconds. It is as if the universe whispers, "You may rush forward, but I will slow your heartbeat so that balance is kept." What then of the ultimate limit? If even modest speeds can stretch time, what would happen as we approach the speed of light? Could the stretching go on forever, until seconds dissolve into stillness? This is the quiet question that invites us onward. As we drift further into the story, let us keep this image in mind. A train sliding out of a station, two clocks comparing notes, a satellite adjusting its rhythm to match the Earth below. These are simple, ordinary things, yet hidden inside them is the extraordinary truth that time is not rigid. It bends, it flexes, it carries each traveller in a slightly different way. From here, the story opens into the foundations of this strange behaviour, the energy barrier that keeps us from catching light, and the invisible geometry of the universe that allows time to stretch but never quite break. If we let the path guide us onward, we come to a shimmering threshold, the speed of light itself. It is the ultimate pace of the universe, the fastest anything can travel, the constant heartbeat woven into every corner of space-time. But why should there be a limit at all? Why not go faster, faster still, until speed is infinite? The answer carries us into some of the most delicate mysteries physics has revealed. Imagine you are standing by a still lake at dawn. The surface of the water is perfectly calm, a mirror reflecting the sky. You toss a pebble, and ripples spread outward in perfect circles. No matter where you stand, no matter how you move, those ripples travel through the water at the same steady pace. They don't slow down to let you catch them, and they don't hurry to escape. Light in many ways is like those ripples, though instead of travelling through water, it moves through the fabric of space itself. When scientists measured light carefully in the late 1800s, they found something shocking. No matter who measured it, no matter how fast the observer was moving, the answer was always the same. The speed of light in a vacuum never changed. It was as if the universe had decided that this one number, roughly 300,000 kilometers every second, was sacred. Einstein took this fact seriously. If light's speed is always the same, he reasoned, then something else must bend to make the math add up. And that something turned out to be time and space themselves. When you try to chase light, the universe doesn't allow you to catch it. Instead, your time slows down, and your lengths shrink in the direction of motion. The harder you push, the more these distortions grow. Think of it like running after your own shadow. No matter how fast you sprint, your shadow stays ahead. You may strain, sweat, and gasp for air, but the shadow never falls behind. Light is like that, always keeping its pace, never letting you draw level. This leads to an extraordinary barrier. Objects with mass, like you, me, spaceships, or even grains of dust, require more and more energy to move faster. At everyday speeds, this isn't noticeable. You push a bicycle, it goes faster. You push harder, it speeds up again. But the closer you come to the speed of light, the more stubborn the universe becomes. Your bicycle, your spaceship, your very body resist acceleration. It's as if the universe adds invisible weights with every increase in speed. Physicists sometimes describe this with the idea that mass increases as you approach light speed. Not that your body literally grows heavier, but rather that it takes more and more effort to add the same tiny increase in velocity. The energy you would need climbs higher and higher, like a mountain that grows steeper the further you climb, and at the very peak, at the exact speed of light, the mountain wall becomes vertical, infinite. To actually reach that summit, you would need infinite energy. And infinity is not something any rocket, star, or universe can supply. So here is the paradox in gentle words. Light speed is not just very fast, it is the boundary where the very rules of physics hold their line. Matter may approach it, lean toward it, inch closer and closer, but never touch. Like a horizon in the desert that recedes as you walk, the speed of light remains forever out of reach. Let's bring this down to an everyday anchor. Imagine pushing a child on a swing. Each push makes them go higher. At first, the difference is obvious, but as they approach the highest point the swing can reach, your pushes add less and less. Finally, there is a natural limit. No matter how strong you are, the swing will never go higher than its chains allow. Reaching the speed of light is like trying to push past those chains. The rules of the cosmos are the chains themselves. Another way to picture it is with honey. Imagine a marble rolling through a thin layer of honey. At first, it moves easily, but as the honey thickens, it slows. By the time the honey is infinitely thick, the marble cannot move at all. For objects with mass, the universe becomes thicker and thicker as they approach light speed, until the effort required becomes infinite. So while photons, the tiny particles of light, glide effortlessly at this maximum speed, you and I cannot join them. Photons are born massless. They do not need to climb the energy mountain, they live on the summit already. For them, travelling at light speed is not an achievement, it is simply their nature. There is a quiet beauty in this. The same light that streams from the sun to warm your skin, that reflects off the pages of a book, that glimmers in the night sky, is not rushing in the way we think of rushing. For light, there is no alternative pace. It does not start slow, then speed up. It is always, forever, steady at its limit. And so, the speed of light stands as a cosmic rule. It is the line drawn through the fabric of reality that says, here and no further. It is not a punishment, not a cage, but simply the way the universe keeps its balance. Without this limit, the harmony of time and space would unravel. Causality, the gentle order of cause and effect, would break. Messages could arrive before they were sent. The arrow of time, which quietly keeps us moving from past to future, would lose its direction. As we drift further into the story, we can let this truth settle gently. The speed of light is not just a number in a textbook. It is the very heartbeat of the universe, steady and unwavering. Every sunrise, every rainbow, every glimmer of starlight carries within it this cosmic rhythm. And it is this rhythm that sets the stage for all the wonders we will explore. How time stretches, how particles live longer, how black holes pull seconds into near stillness. From here, the trail of clues leads us into the delicate dance between time and speed, where the simple act of moving reshapes the seconds themselves. If we lean closer to the edge, we will see how time begins to slow, softly and strangely, as if pausing to catch its breath the faster we try to go. The trail of clues now carries us toward one of the most delicate and beautiful consequences of Einstein's insight: time itself slowing down for those who move quickly. This idea, called time dilation in physics, sounds almost like science fiction. Yet it is real, measurable, and quietly unfolding around us every day. To begin, let's take a simple picture. Imagine two friends, each are holding a small glowing clock. One stays at home, sitting by the window with a cup of tea. The other steps into a sleek train that begins to glide along the tracks. From the perspective of the friend at the window, the train gathers speed, its wheels humming softly. The friend inside, however, feels at rest. They sip their tea, glance at their glowing clock, and see it tick as always, steady, reassuring, ordinary. Now, here is where relativity reveals its gentle trick. When the friend at the window peeks at the moving clock through the glass, they see something peculiar. To their eyes, the clock on the train is ticking more slowly than their own. Seconds stretch. Time itself seems to run at a different pace for the traveller. Yet for the traveller, nothing unusual is noticed. Their heart still beats in rhythm. Their tea still cools at the same pace, and their clock appears faithful. Time, in other words, is loyal to each observer, but when compared side by side, the difference emerges. This is not simply an illusion. It has been measured again and again. Scientists call the amount of slowing the Lorentz factor, a mathematical way of showing how time stretches with speed. But we need not fuss over the formula. Think instead of a rubber band. The faster you move, the more the rubber band of time stretches. At everyday speeds, walking, driving, even flying in an airplane, the stretch is too small to notice. But as you creep closer to the speed of light, the band stretches more and more, seconds elongating like strands of taffy pulled in slow motion. An everyday anchor helps here, the satellites circling above Earth, which guide your phone's maps. Each one carries clocks so precise they can measure billionths of a second. And yet, these clocks tick differently than those on the ground. Because they are moving quickly and are in a weaker pull of Earth's gravity, their time flows at a slightly altered pace. Without constant correction, your GPS would point you to the wrong street, the wrong cafe, the wrong corner of the city. In a quiet way, every journey you take with your phone is proof that time is flexible. But perhaps the most haunting way to feel this truth is through a thought experiment often told by physicists, the tale of two twins. Imagine one twin stays on Earth, living through years of birthdays, seasons, and quiet evenings. The other climbs aboard a spacecraft and journeys close to the speed of light. For the travelling twin, time flows as usual. Heartbeats, laughter, thoughts, all ordinary. But when they return, they find their sibling older, changed, living in a world that has aged more than they have. What felt like a brief voyage for one was a long unfolding of years for the other. This is not fantasy. It is the logical consequence of time stretching at high speeds. Even particles in the cosmos live out this paradox. High above Earth, cosmic rays strike the atmosphere and create fleeting particles called muons. These should vanish almost instantly, gone before they can travel even a short distance. And yet, many of them reach the ground, as if their lives were prolonged. The reason is not that they live longer in their own world, they still tick to their own short rhythm. It is that to us, watching from below, their clocks are slowed. The muons make it to Earth because time itself stretched for them while rushing near light speed. Think of the quiet poetry in this. Tiny messengers from space, normally so fragile, are granted longer lives simply because of their speed. It is as though the universe bends time to carry them further, giving them a journey they could never otherwise complete. For us humans, the effect is nearly invisible in daily life. Riding a bicycle or flying in a jet does not make your watch noticeably lag. But in the vast scales of the cosmos and in the precision of modern science, the stretching of time is undeniable. It whispers that our most basic sense, that a second is always a second everywhere for everyone, is not the whole story. There is a calm paradox here. Time is deeply personal. To you, it never feels distorted. You cannot sense your own seconds stretching, and yet when compared across different paths, different speeds, the differences appear. Relativity teaches us that time does not exist as one universal rhythm, but as a symphony of rhythms, each instrument playing its own pace depending on its journey. Let's soften this with one more image. Picture two candles burning. One stands still on your desk, flame steady in the air. The other is placed on a fast-moving train, its light flickering through the window as it speeds by. To each observer, the candle seems to burn as normal. But if you could compare them with impossible precision, you would find that the candle aboard the train lasted longer. Its seconds stretched. Its story took more time to complete. This is the gentle strangeness of time dilation. From here, we may ask, how far can this stretching go? If the band of time stretches more and more with speed, could it ever stretch so far that it snaps, freezing altogether? Could seconds vanish, leaving only stillness? That is the edge we are walking toward. Our quiet exploration now turns to the energy barrier, the invisible wall that keeps us from ever reaching the speed of light, the reason why we can only approach but never touch the place where time might stop completely. The path now carries us into a quiet but unyielding truth. No matter how hard we try, no matter how powerful our rockets, or how ambitious our dreams, nothing with mass can ever reach the speed of light. It is not a matter of engineering, or of building a stronger engine. It is woven into the very fabric of physics, as permanent as the horizon. And the reason lies in the way energy and speed dance together. To begin, imagine you are pushing a sled across snow. At first, each push sends it gliding further. The more effort you give, the faster it goes. But after a while, the snow becomes deeper, heavier. Each shove adds less and less speed. You strain harder, sweat drips down your back, and still the sled inches, forward only reluctantly. The closer you try to get to light speed, the more the universe feels like that deep snow, resisting you with invisible heaviness. Physicists describe this with mathematics, using something called the Lorentz factor. But let's keep the numbers soft. The essence is simple. The faster you go, the more energy is needed to make the same small increase in speed. At ordinary speeds, this is easy to overlook. Cars accelerate, planes take off, rockets roar into the sky. But as we climb closer to the speed of light, the cost rises steeply. Each gain demands more and more until at the final approach the energy required is infinite. Infinity is not just a lot. It is unreachable, untouchable, like a horizon that recedes as you walk toward it. Think of climbing a mountain. At first, the slope is gentle. You can walk with ease, even jog if you wish. As you ascend, the air thins, the incline grows steeper, your steps shorten. The summit still looks close, but every step costs more breath, more strength. Now imagine that as you climb, the mountain itself grows taller, steeper, endless. No matter how high you reach, the summit pulls further away. That is what it means to approach light speed. The universe itself stretches the mountain of effort until no traveller of mass can reach the top. Some people find this idea disappointing. Shouldn't we, with enough technology, eventually break through? But the barrier is not an engineering problem. It is part of the geometry of space-time itself. The chains that hold the swing, the honey that thickens around the marble, these are not things we can cut or thin. They are the rules by which the cosmos keeps order. There is a deeper beauty here too. If it were possible to surpass light speed, causality itself, the orderly flow of cause and effect would unravel. Imagine sending a message that arrives before you type it, or watching a glass shatter before it slips from your hand. Without the barrier, time would lose its arrow, and the universe would become a place where events no longer made sense. The energy wall is not only a physical limit, it is also a safeguard, preserving the gentle logic of before and after. Let's bring this down to a more familiar anchor. Think of a swing in a playground. Each push makes it climb higher, until the chains pull taut. You can pump harder, push stronger, but the swing will never go beyond that arc. The chains define the limit. Similarly, no matter how powerful our rockets or engines, the universe holds its chain, the speed of light. Or picture pouring water into a glass. At first, the glass accepts it easily, but as it nears the brim, each drop threatens to spill. At the very edge, no more can be added without overflow. Trying to reach light speed is like trying to fill that last impossible drop. It simply cannot be done without breaking the rules of the vessel itself. And yet, this impossibility is not discouraging. Instead, it points us toward a deeper wonder. Light is not like us. It has no rest mass to carry, no weight to slow it down. It was born to travel at its ultimate pace. When we watch a sunrise or glimpse a star's sparkle across the night, we are seeing the effortless motion of something that never struggled against the energy barrier. For light, there is no climbing, no strain, no resistance. It simply is. The lesson here is both humbling and profound. The universe does not give us everything. It places limits, firm and immovable. But in those limits lies order, beauty, and the chance to understand. By recognizing that we cannot reach light speed, we come to appreciate the quiet flexibility of the speeds we can achieve and the soft stretching of time that already greets us as we move faster and faster. And so, our footsteps pause at this invisible wall. We cannot pass through, but we can lean close. We can watch the way time bends, the way particles live longer, the way clocks disagree. All of this happens long before we reach the impossible limit. The wall may stand eternal, but the journey toward it is filled with treasures. As we drift further into the story, let us carry with us this picture. A mountain that grows taller the higher you climb, a swing bound by chains, a glass that can never hold the final drop. These are gentle metaphors for the same truth. The speed of light is the summit we cannot stand upon, but it shapes the landscape of everything we see. From here, our quiet exploration turns to how this energy wall changes the flow of time itself. If the closer we come to light, the more seconds stretch, then perhaps we can glimpse what it means for time to approach stillness. Could we imagine a world where a second lasts forever? The next step brings us into that delicate threshold. If we follow the thread further, we arrive at a curious shape hiding in the mathematics of relativity. Physicists call it the Lorentz factor. To them, it is a neat symbol tucked into equations, but for us we can imagine it as a stretching curve, a quiet line on a graph that tells the story of how time bends the faster you move. At first, this curve rests calmly near the bottom, hardly rising at all. At walking pace, at driving pace, even at the speed of a passenger jet, the curve is almost flat. The stretching of time is too tiny to see, like the slow drift of a shadow across a garden wall. But as you push faster, the curve begins to rise, and then more steeply, as if a gentle hill suddenly becomes a cliff. Near the speed of light, the line shoots upward, climbing toward infinity, refusing to level out. It is here that the language of physics whispers its quiet warning. As you near the ultimate speed, the seconds themselves begin to stretch without limit. We can soften this picture with something familiar. Imagine trying to run through thick honey. At first, you can push your way forward, sticky but possible. With each step, though, the honey seems to resist more and more. Your legs slow, your arms strain, the effort climbs. Now imagine the honey becoming thicker and thicker until, at some final moment, it hardens entirely. No matter how you push, you cannot move faster. This is what the Lorentz factor is telling us. Not with stickiness, but with time. The faster you go, the more time resists, until at light speed, time stretches so much that it would take infinite effort to push further. Another way to feel it is to picture yourself in a dream. You're running down a corridor, but the faster you pump your legs, the slower the scenery passes. It is as if the world itself conspires to hold you back, letting your effort grow, but letting your progress fade. The Lorentz factor is that dream corridor written into the mathematics of reality. Of course, in the actual equations there are symbols, a letter V for velocity, a letter C for the speed of light, and a square root that makes the number rise steeply as velocity approaches c. But you do not need to see those symbols. It is enough to imagine the rubber band of time stretched further and further as speed climbs, until it seems almost ready to snap. Yet it never does. It simply stretches more and more without end. This steepness has been measured, not in dreams but in laboratories. Particles hurled near light speed live longer than expected. Clocks flown on fast airplanes return home ticking ever so slightly behind. These are small glimpses of that rising curve, proof that the Lorentz factor is not just a symbol, but a real companion to motion. Think of how strange and yet comforting this is. Time is not rigid, it is elastic, like a fabric that yields under pressure. But it yields only in one direction. It slows, never speeds up. The faster you move, the more carefully the universe lengthens your seconds as if to preserve balance. We might ask, why? Why should time behave this way? The answer lies in the insistence of light itself. Because light refuses to change its speed for anyone, space and time must do the bending instead. And the Lorentz factor is simply the way of describing how great that bending becomes as you move closer to the cosmic speed limit. Perhaps we can picture the universe itself as a quiet caretaker. It allows you to run, to fly, to accelerate as much as you like. But as you near the boundary, it gently lays a hand on your shoulder and slows your heartbeat. You may rush, it seems to whisper, but your seconds will stretch. You cannot break the rhythm that light has set. Everyday life hides this truth well. Walking to the kitchen does not stretch your seconds enough to notice. Driving a car does not make your clock fall behind. Even an airplane, circling the Earth, produces only tiny delays, measured in nanoseconds, billionths of a second. But those billionths are real, and when speeds climb to fractions of light itself, those billionths swell into minutes, hours, even years of difference. So, when physicists speak of the Lorentz factor, we need not imagine a cold formula. We can imagine instead a steep hillside, a runner in honey, a dream corridor that slows as you try to sprint. These images carry the same meaning. The closer you come to light speed, the more the universe stretches your time until it approaches stillness. Let's pause with one final image. Picture holding a rubber band between your fingers. At first, it resists only slightly. You pull, it stretches easily. But as you keep pulling, the tension grows. The band becomes tighter, harder to stretch further. At last, the effort needed to lengthen it more would be impossible. Your fingers ache, the rubber trembles, and though you could strain forever, the band would never yield that final bit. The Lorentz factor is the invisible rubber band of time. We live our days near the slack end, barely noticing its pull. But out there, at the edge of light, it tightens endlessly, guarding the boundary with infinite resistance. As we drift further into the story, we will see how this stretching is not just a curiosity for physicists. It has consequences we can imagine in human lives. It becomes the tale of two siblings, one journeying to the stars at near light speed, the other staying behind. When they meet again, the rubber band of time will have pulled differently for each, leaving them separated not by distance but by years. If we follow the thread a little further, the gentle slope of stretched time opens into a story, perhaps the most famous story in all of relativity. It is sometimes called the twin paradox, but the word paradox is a little misleading. It's not a contradiction at all, but a natural unfolding of the way the universe bends time. And told softly, it becomes almost like a bedtime tale of two siblings who choose different paths beneath the stars. Imagine then two twins. Let's call them Mira and Sul. They are born together, grow up together, sharing birthdays and candlelit cakes. One day, Mira decides to stay on Earth, while Sul dreams of travelling among the stars. When the day comes, Sul boards a spacecraft built to travel near the speed of light. The engines hum, the stars blur, and soon Sul is sailing far beyond the familiar blue sky. For Sul, inside the ship, time flows as it always has. Heartbeats follow one another. Meals arrive at ordinary intervals. Conversations with the onboard computer take place in a normal rhythm. Nothing seems unusual. Sul writes in a journal, gazes at the stars and thinks of home. Back on Earth, Mira continues life's gentle pattern. Seasons changing, trees blossoming and fading, years slipping by. To her, time flows in its ordinary familiar way. She grows older, hair silvering, steps softening. Now comes the twist of relativity. When Sul finally returns, stepping down the spacecraft's ladder and walking once again onto Earth's soil, Mira is much older. Perhaps she has grandchildren. Perhaps entire decades have passed. Yet Sul, though aged, has lived through far fewer years. The traveller has become the younger twin. The siblings who once shared every birthday now stand apart, separated not by love or distance, but by time itself. To many people, this sounds impossible. How can two people born together live through different amounts of time? The answer lies in the stretching of seconds along Sul's journey. Because Sul was moving so close to light speed, Sul's seconds were lengthened compared to Mira's. Each heartbeat, each breath, each journal entry took place within that stretched fabric. Sul never noticed. It felt completely normal. But when measured against Mira's slower, steadier earthbound time, the difference revealed itself. This is the heart of what some call the paradox. Each twin experiences time personally, loyally, without distortion in their own frame. But when their paths reunite, the comparison shows a gap. Time itself has carried them differently. We can soften this with everyday anchors. Imagine returning home after a long trip abroad. To you, it may feel like a brief adventure, just a few months perhaps. But when you arrive, you find the garden has changed, friends have moved away, and children you once knew are suddenly taller. The world seems to have leapt ahead while you were only gone for a short while. This is only an echo of the twin story, but it gives the same feeling. That unsettling yet beautiful moment when you realise the flow of time has not been the same for everyone. Another image. Picture two rivers flowing side by side. One takes a direct path, steady and smooth. The other winds through long bends, slowed by rocks and waterfalls. Both rivers begin at the same mountain spring, but when they rejoin at the valley below, one has travelled farther in time than the other. This is how Mira and Sul's lives diverge and meet again. It may comfort you to know that physicists have tested this story. Not with human twins, of course, but with clocks, which serve as faithful stand-ins. In the 1970s, scientists placed extremely precise atomic clocks on airplanes that circled the globe, while identical clocks remained on the ground. When they compared the times afterward, they found exactly what relativity predicts. The airborne clocks had ticked a little more slowly. The difference was tiny, fractions of a microsecond, but it was real. In principle, if the journey were faster and longer, the difference would grow into years, decades, even centuries. So the twin paradox is not a fantasy. It is a real glimpse into what happens when motion bends time. In the everyday world, the effect is small, but in the cosmos, at near-light speeds, it becomes astonishing. There is also a poetic note here. The paradox reminds us that time is not absolute. It is personal, woven into each journey. Saul and Mira each lived fully, each carried faithfully by their own seconds. Neither cheated, neither lost time. They simply followed different paths across the fabric of space-time, and when those paths rejoined, the fabric revealed its quiet asymmetry. Let's pause to let that sink in. Two people, born together, could one day stand side by side with different ages, not because of magic, not because of trickery, but because time itself has no single rhythm. It dances differently for each traveller, depending on how fast and how far they have moved. You might wonder, does this mean one twin experienced less life? Not at all. Saul felt every moment, every thought, every dream. To Saul, the years away were full and rich. It is simply that Mira's earthly clock marched more quickly. Life is not shortened or diminished. It is simply measured differently by different paths. If you close your eyes, you can imagine it softly. One twin stepping out of a spacecraft, the other waiting with lines of age on their face, both smiling, both remembering their shared childhood. Different ages, yet still connected by love and memory. In the end, relativity does not separate them. It shows that even across such differences, the bond of experience remains. As our quiet journey continues, the trail now carries us toward another strange twist. Not only time, but space itself bends and contracts when you move quickly. If Saul's seconds stretched out, Saul's distances also shrank in the direction of travel. The universe does not only slow your clock, it also reshapes the stage beneath your feet. That is the mystery we will step into next. From here, our quiet exploration turns to something even stranger than stretched time. Relativity does not only change the ticking of clocks, it reshapes space itself. As you move faster and faster, not only do your seconds lengthen, but the very distances you travel begin to shrink. This effect is known as a length contraction, and though it may sound like a magician's trick, it is as real as the slowing of time. Let's begin with an image. Imagine holding an old accordion. At rest, its folds are stretched open, long and spacious. Now gently press the sides together. The folds squeeze. The distance between the ends becomes shorter, yet the accordion itself is not broken. In relativity, motion acts like your hands pressing the instrument. As an object moves faster, the universe gently squeezes it in the direction of travel, shortening its length as seen by an outside observer. To make it more personal, picture running down a long hallway. When you walk, the hallway seems to stretch on normally, each step carrying you forward at an easy pace. But as you sprint, your perspective changes. The far end seems closer, the walls blur, the distance feels compressed. Of course, in everyday life, this is only an illusion of perception. But relativity tells us that at speeds near light, the shrinking of space is not an illusion. It is built into reality. For someone moving at such speeds, their own sense of size and distance feels unchanged. Inside the spaceship, the traveller still measures the craft as the same length, feels the same stride, experiences no squeeze at all. But to the person watching from outside, the ship appears shorter along its line of motion. Time dilates for the traveller and space contracts around them. Together, these two distortions, time and space, keep the speed of light as the unbreakable limit. There is a quiet elegance in how this works. Time slows, space shrinks, and yet the universe remains balanced. Imagine carrying a tray of water glasses. If you tip one side, the liquid sloshes, but tip the other side at the same time, and the water steadies. Relativity works like this balance. The stretching of time and the contracting of space tilt in just the right way to preserve harmony. You might ask, have we ever seen this in practice? The answer is yes, though not with spaceships. Particle accelerators, vast rings of machinery where scientists hurl tiny particles near light speed, offer a glimpse. When particles move so quickly, the distances they seem to travel, the paths they take, and the very lifetimes they live are all shifted by these relativistic effects. Without taking length contraction into account, the experiments would make no sense. Another way to soften this idea is to think of folding paper. Place 2 dots on opposite ends of the sheet. At rest, the dots are far apart. Now fold the paper so the dots touch. The distance between them has collapsed, even though the paper itself remains whole. Relativity, in a sense, performs this fold whenever motion nears light speed. To the moving traveller, the journey feels normal. To the outside observer, the distance itself has shrunk, allowing the traveller to cross in less time. There is a gentle poetry in this. Speed does not only carry you forward more quickly, it alters the stage beneath your feet. Distances shrink. Horizons come closer. The universe itself rearranges so that light remains the faithful limit. It is as if space and time conspire together, whispering, "We will bend ourselves rather than let you outrun light." This raises a curious thought. Could length contraction make distant stars feel closer? In a sense, yes. For a traveller moving at near light speed, a galaxy that seems millions of light years away to us might appear much nearer, because space itself has compressed along the line of motion. The journey would still take enormous time from our perspective, but to the traveller, the road would have shortened. It is another reminder that distance is not absolute. Like time, it is woven into the relative fabric of motion. Let's pause with a gentle anchor. Imagine again the accordion. When at rest, it breathes open, long and wide. In motion, the hands close it, squeezing the folds together. Space itself, under motion, behaves this way. Not broken, not torn, but quietly reshaped. Or think of a hallway in a dream, which stretches when you walk and compresses when you run. Reality, it turns out, carries a touch of that dreamlike quality at the cosmic edge of speed. What matters most is that this contraction, combined with the slowing of time, keeps all observers in agreement that the speed of light is untouchable. Each traveller feels their own distances and seconds as perfectly ordinary. But when compared, the differences reveal the hidden geometry of the universe. There is a soft humility in this discovery. We're used to thinking of space as fixed, rigid, absolute. But in truth, it flexes, yields, and adjusts in perfect partnership with time. Together they preserve balance, ensure causality, and allow the cosmos to unfold without contradiction. As we drift further into the story, we will step out of thought experiments and into evidence from the cosmos itself. We will meet tiny particles that should die in a blink but live long enough to rain upon the Earth. We will see how even your phone depends on Einstein's insights to tell you where you are, and we will glimpse how black holes, those silent giants, slow time in ways almost unimaginable. For now, let this thought settle softly. Motion reshapes both the seconds we live and the distances we cross. We carry space and time with us as we move, and they in turn bend themselves to carry us. The trail of clues leads us now from imagination into evidence. It is one thing to picture twins aging differently or hallways shrinking in dreams, but another to see proof written into the particles of the universe itself. And one of the clearest, most poetic demonstrations of relativity comes from tiny fleeting messengers called muons. Muons are born high in Earth's atmosphere. They appear when cosmic rays, energetic fragments from distant galaxies, slam into the thin air miles above our heads. In that collision, a shower of new particles is created like sparks from flint. Among them are muons, cousins of the electron but far heavier. They are fragile beings, with lives measured in millionths of a second. According to what we once believed, they should vanish almost as soon as they are born. Here is the puzzle. Those muons are born so high above Earth that, even racing close to the speed of light, they should decay long before reaching the ground. If their lifetimes were fixed and rigid, our detectors on the surface would find almost none. And yet, when physicists set up instruments to measure them, they found streams of muons arriving from the sky. Far more than expected. It was as if these fragile sparks had been granted extra time to complete their journey. The explanation lies in the stretching of time. For the muons themselves, their clocks tick normally. Each one lives its natural span, no more, no less. But to us on Earth, watching their flight, those brief seconds have been elongated by motion. The faster they travel, the more their seconds stretch, allowing them to survive the long trip from sky to soil. Think of a candle that should burn out in an instant. Light the wick, and in the blink of an eye it should fade. But if the candle were carried on a rushing wind, its flame would appear to last longer, glowing as it crossed the distance. The flame has not changed. It is still burning at its normal rate. But to us, watching from the ground, the candlelight lingers. The muons are like that candle, their brief lives stretched by speed into something longer than expected. This is not a thought experiment. It is measured fact. Cosmic rays rain upon us constantly, and detectors record muons arriving at the surface every day. Without time dilation, they would wink out long before we could greet them. Their very presence is a signature written by Einstein's theory into the sky above us. And there is more. In laboratories, scientists recreate the same effect. They accelerate particles to near-light speed in long underground rings and watch as their lifetimes expand. Particles that should decay in millionths of a second live 10 times longer, 100 times longer, all because their motion bends the flow of time. The Lorentz factor, that steep curve we imagined, becomes visible in data points on a scientist's chart. But for us, it can be felt in the poetry of muons showering Earth, arriving like travellers who are given just enough extra time to complete their journey. There is a gentle irony in this. Humans often dream of extending life, of living longer than nature intended. Yet here in the high atmosphere, particles achieve that miracle simply by moving faster. They do not ask for more time, but relativity grants it. Their fragile existence is preserved just long enough to touch the Earth. Let's pause with another anchor. Picture a mayfly, a creature whose adult life may last for only a single day. Imagine one caught in a strong breeze, carried swiftly across a meadow. Though its own tiny clock ticks the same, to us, watching from the side, its day seems to stretch out, giving it more flight, more presence. That is what motion does for muons. Their mayfly lives, extended by speed, reach the ground to tell their story. In a sense, the muons are the universe's proof that time dilation is not an abstract idea, but a real, physical truth. They are little cosmic postcards from relativity, falling from the sky to remind us that our seconds are not absolute. They whisper, time bends, time stretches, even in the tiniest lives you can see it. And the beauty is that this proof arrives for free, no expensive telescopes required. You can build a simple muon detector with the right equipment, and it will click softly as these extended travellers pass through. Each click is a reminder that the universe is stranger and more flexible than it seems. When you next look up at the night sky, imagine the invisible rain of muons cascading through the air. Imagine their clocks stretched by motion, their fragile sparks lengthened into journeys. They are living examples of how speed bends time, a quiet rain of evidence falling upon the Earth. As we drift further along this path, we can take comfort that relativity is not only written in faraway galaxies or complex equations, but in the very air around us. Time is elastic, and the muons prove it every second. From here, our journey carries us to an even more familiar anchor. You don't need to catch cosmic particles to see relativity in action. You already carry it in your pocket. The satellites that guide your phone's maps depend on relativity to stay honest. Without Einstein's insights, your pizza delivery or evening walk would quickly become lost. Our quiet exploration now turns to those satellites circling above, where time ticks just differently enough to keep us on the right path. Our quiet trail of evidence now drifts from cosmic particles in the sky to something far more familiar: satellites orbiting silently above us. We rarely notice them, but their presence is stitched into our daily lives. They guide airplanes across oceans, ships through harbours, and perhaps most often, they guide you when you glance at the glowing blue dot on your phone, wondering where exactly you are. And here is the gentle truth: that blue dot would wander uselessly if not for Einstein's theory of relativity. Each satellite in the global positioning system carries extremely precise atomic clocks. These clocks tick with remarkable steadiness, like the heartbeat of the heavens. But the moment they were launched into orbit, those beats no longer matched the clocks we keep on the ground. They began to drift, not because of faulty engineering, but because of the bending of time itself. Two effects shape this drift. First, the satellites are moving quickly around Earth. And as we've seen, motion stretches time. A clock in motion ticks a little slower compared to one at rest. But there is also a second effect. Satellites are far above Earth's surface, where gravity is weaker, and gravity too bends time. Clocks in weaker gravity run a little faster than those under stronger pull. The combination is subtle but decisive. The motion of the satellites makes their clocks tick slower, while their distance from Earth's gravity makes them tick faster. Both effects must be measured and balanced. Left uncorrected, the differences would cause the satellite clocks to drift by microseconds each day. That may sound tiny, but even a few billionths of a second translates into kilometers of error on the ground. Your phone might place you in the wrong neighborhood, or send a delivery driver circling hopelessly far from your home. Here lies the gentle humor of it. Pizza delivery, ride-hailing, walking directions, all depend on Einstein. Without the corrections of relativity, your food might never arrive hot. Your taxi might never find you, and your quiet evening walk could end in confusion blocks away from where you intended. The abstract ideas born in a patent office in 1905 have become the silent guardians of modern convenience. Think of that the next time you open your Maps app. A signal leaves the satellite racing at the speed of light toward your phone. Your phone measures how long the signal took to arrive, and from that it estimates your distance from the satellite. But if the clocks disagree, even by a fraction of a microsecond, the calculation falls apart. Your phone may think you're standing in the river when you're on the bridge, or inside a stranger's house instead of your own. Precision is everything, and relativity provides the corrections that keep the system honest. It is humbling to realize that relativity is not only proven in remote laboratories or cosmic showers of muons, but in your pocket guiding you through the streets. The universe's strange rule, that time bends with motion and with gravity, is woven into the very act of finding your way to the nearest cafe. We can soften this with a simple anchor. Imagine trying to bake bread, but your kitchen clocks all tick at slightly different rates. One tells you 10 minutes have passed, another insists 15, and the third is convinced only 5. If you trust the wrong clock, your bread is burnt or undercooked. GPS satellites face the same problem. Each one carries a clock, but without relativity, they would all fall out of step. It's only by adjusting them, by accounting for the slower ticks of motion and the quicker ticks of weaker gravity, that your phone receives a coherent recipe for where you are. Engineers and scientists account for these effects constantly. The system corrects itself in real time, weaving the two distortions into one accurate whole. It is a quiet, ongoing dance between speed and gravity, written into equations but felt in your everyday movements. And perhaps there is poetry here too. Every time you see that little blue dot sliding across the map, you are seeing the bending of time in action. Not as a metaphor, not as a story, but as a living truth. Each step you take is guided by satellites whose seconds are not quite the same as yours, but adjusted so that the world can remain in harmony. This should remind us of something important. Relativity is not a distant theory. It is not confined to black holes or particle accelerators. It is part of the air we breathe, the ground we walk, the devices we hold. It is stitched into modern life, invisible but essential. Without it, the modern world would stumble. So when we think of Einstein's ideas, we might picture chalkboards filled with symbols or physicists deep in thought. But perhaps we should also picture a delivery driver following directions, a traveller finding their hotel, or a child using a map to catch a bus. All of them, unknowingly, are living in a world where time is elastic, where clocks tick at different rhythms, where the strange dance of relativity quietly keeps everything in order. As we drift further into the story, the path will take us to another cousin of this phenomenon. If motion can stretch time, so too can gravity. The deeper the well of gravity, the slower time flows. Near the surface of Earth, the effect is small. But near the crushing presence of a black hole, it becomes almost unimaginable. Let us now turn gently toward gravity's hand on time and see how it mirrors the bending we have already come to know. Our quiet exploration now turns from motion to gravity. We've seen how speed can stretch seconds, how the faster you go, the longer your time becomes compared to others. But speed is not the only hand that can tug on time. Gravity has its own grip, just as steady, just as strange. And together the two create a symmetry in the way the universe bends the flow of moments. Imagine, if you will, a blanket laid gently across a bed. Place a small pebble on it, and the blanket sags only slightly. Place a heavy stone, and the sag deepens. Drop a mountain there, and the fabric sinks dramatically, pulling everything else toward the center. Space and time behave like that blanket. Wherever there is mass, the fabric bends, and in that bend, time itself slows down. Near the surface of Earth, the effect is subtle. Clocks at sea level tick ever so slightly slower than clocks placed on mountaintops. The difference is tiny, far too small to notice with your eyes, but real nonetheless. Time flows just a fraction faster for someone standing on a high plateau than for someone living at the shore. It is as if the Earth holds your seconds more tightly when you're closer to its pull. Let's anchor this in something more personal. Think of lying under a heavy blanket on a cold winter night. At first it feels comforting. The weight presses gently, slowing your movements, keeping you warm. The thicker the blanket, the heavier the press, until eventually you can hardly move at all. Gravity does this to time. The stronger the pull, the heavier the blanket, the slower time slips by. This effect grows dramatic near extreme masses. Imagine standing near a black hole, a place where gravity becomes so strong that even light cannot escape. There, the blanket of space-time is pulled so deep it might as well be bottomless. For someone circling near its edge, time itself slows almost to a standstill compared to a distant observer. Seconds stretch into minutes, minutes into years. A person orbiting the black hole could look out and see the universe racing forward, galaxies spinning, stars aging, while for them, only moments have passed. This is not a fantasy of science fiction. It is a direct prediction of relativity, and it has been confirmed in smaller ways close to home. Scientists place atomic clocks at different heights, one in a basement, another at the top of a tower, and watch as they fall out of sync. The higher clock farther from Earth's gravity ticks slightly faster. The lower clock deeper in the gravitational well ticks slower. the experiment shows us that time is not a universal metronome. It is elastic, shaped by where you stand and how gravity presses against you. If we combine this with what we've already learned about speed, the picture becomes richer. Time can bend because of motion, and it can bend because of mass. In fact, both effects intertwine in our everyday world. The GPS satellites we spoke of earlier are influenced by both. Their speed makes their clocks tick slower, while their distance from Earth's gravity makes them tick faster. The two influences tug in opposite directions, and engineers must balance them carefully. It is humbling to realise that gravity, which we usually imagine as a force that pulls apples from trees and keeps our feet on the ground, also pulls on something invisible and intimate, the seconds of our lives. It does not yank them suddenly. Instead, it stretches them softly, like taffy pulled in slow motion, or like the dragging weight of a heavy quilt. Let's pause with another image. Imagine you are swimming in a calm lake. Near the surface, you move easily, the water barely resisting. But as you dive deeper, the pressure builds. The water presses more tightly, making each movement harder, slower. Time behaves this way in a gravitational field. Near the surface of Earth, the pressure is light, the seconds flow normally. But as you move deeper into gravity's well, the pressure grows and time slows. In the grand scales of the cosmos, this slowing becomes profound. Near a black hole, if you were to watch from a safe distance, you would see your companion's time nearly freeze as they approached the event horizon. To you, their movements would slow, their signals would stretch, until at last they seemed to hover forever at the edge, never quite falling in. But for them, time would continue faithfully, carrying them across that horizon with no awareness of the outside view. This is one of the gentle paradoxes relativity offers us. Different observers, each living their own personal time, can disagree about how much has passed. And both are right, for time is not one absolute river, but many small streams flowing through the fabric of space-time. So we now see that relativity has two cousins, speed and gravity, each with the power to stretch and bend time. Both whisper the same truth. The seconds we live are not rigid or universal, but flexible, loyal only to the path we take and the place we stand. And perhaps there is a quiet lesson here too. In our own lives, time often feels heavy, slowed by burdens or quickened by joy. Science shows us that even in the cosmos, time is not fixed. It bends, it yields, it flows differently depending on the weight upon it. In that sense, our personal experience of time's elasticity mirrors the universe itself. As we drift further along this journey, the next step carries us to the very edge of light itself. We will ask what it means for photons, those tiny sparks that always move at light speed, to experience no time at all. For them, there is no before, no after, no waiting, no growing older. The stage now opens to the strangest idea yet. What does it mean to exist in a world where time never flows? The trail of our journey now brings us face to face with the strangest traveller in the universe, the photon, the particle of light. Everything we have spoken of so far, seconds stretching for astronauts, space squeezing for speeding ships, clocks ticking differently in mountain towers and deep basements, has been about those who still move slower than light. But what of light itself forever racing at the cosmic limit? What does time mean for something that is always, without exception, moving at light speed? Here we must pause, for the truth is subtle. Physics tells us that light does not have what is called a rest frame. In gentle words, this means there is no perspective you can adopt where the photon is sitting still, ticking seconds on its own clock. For you and me, no matter how fast we go, we can always imagine slowing down, stopping, catching our breath. Light never does. It never pauses. It never has a speed less than light speed. And because of this, time as we know it, measured in beats of a heart or ticks of a clock, does not apply to photons. Let's soften this with an anchor. Imagine mailing a letter, placing it in the box with its neat stamp. For you, the days in between posting and delivery matter. You wait, you anticipate. But what if the letter could leap instantly into the hands of its recipient? For the letter, there would be no in-between, no waiting, no delay, only the moment of being given and the moment of being received. For photons travelling across the universe, the story is a little like that. From emission to absorption, there is no sense of passage. There is no before and after, only the instant of departure and the instant of arrival. That sounds almost mystical, but it is not speculation. It is a direct consequence of relativity. As objects with mass approach light speed, their time slows more and more. Push the thought to its limit, and if somehow mass could be removed entirely if we were pure photons, then the seconds would stop flowing altogether. Physics calls this zero proper time, but for us it is easier to say, light does not experience the passing of time at all. Let's imagine starlight. A photon born in the heart of a distant star, forged in the heat of nuclear fusion, begins its long journey across space. To us, billions of years may pass before it arrives at Earth. Dinosaurs rise and fall, continents drift, civilizations appear. But for the photon itself, if we could imagine it having a perspective, there is no wait. The birth in the star and the arrival in your eye are the same event, one continuous instant. It is as though the photon never travelled at all, but was always both there and here. Of course, we must be careful. Photons have no awareness. They are not little conscious travellers. To say they experience anything is only a metaphor. But the mathematics of relativity leaves no room for hesitation. The very quantity we call time, measured along a photon's journey, is zero. Perhaps the best way to picture it is with a bridge. Normally when you walk across a bridge you feel the steps, one after another, the rhythm of the journey. But imagine a bridge that collapses so completely that the beginning and end touch. There are no steps, no middle, only the connection. That is what motion at light speed does to time. It erases the in-between, leaving only the link from start to finish. This perspective explains why the universe insists on the speed of a light as a limit. For anything with mass, reaching that place would mean time halts, distance collapses, the rules dissolve. Only the massless photon can inhabit that strange edge, existing without the passage of seconds. Let's rest with a softer metaphor. Imagine a waterfall frozen in mid-air, each droplet suspended as though time had stopped. For us, such an image is a trick of a photograph. For photons, it is reality. They do not flow through seconds. They're always in that frozen state between source and destination. This truth has enormous consequences. It is why light, once released, travels unrelentingly until it is absorbed. It is why we can look at stars across the galaxy and know we're seeing not just distant space but distant time. The photons that touch your eyes tonight may have left their stars before Earth even existed, and yet, for them, there was no delay, no long voyage, no journey through aeons. They were born and they arrived in one timeless instant. There is a quiet wonder in this. When you gaze at starlight, you are touching something both impossibly ancient and yet, in its own frame, impossibly immediate. The light is old beyond measure, yet it has never aged. It is both then and now a timeless visitor slipping through the cosmos. As we drift further along this path, let us hold on to that thought. Time, which feels so unshakable to us, has already been shown to stretch and bend with motion and gravity. But at the very edge, at light speed itself, time disappears altogether. Our next step will draw us even deeper into that thought. If photons exist without seconds, if distances collapse for them, then what does it mean for light to travel at all? Does it move, or is it always already present, linking emission, and absorption, like two dots folded together on a page. That is the mystery we will let unfold as we continue. If we follow the thread a little further, the path opens into one of the most breathtaking ideas of relativity, that for light there is no distance, no duration, no middle ground. From our human perspective, light seems to dash across the cosmos at an incredible pace, yet always taking time to arrive, minutes from the sun, years from nearby stars, billions of years from the edges of galaxies. But for light itself, if we may borrow the language of imagination, none of that exists. There is no waiting, no travelling, no between. Let's return to the bridge image. Normally a bridge is a span. You walk across it step after step, feeling the boards beneath your feet. Each step is a second, each railing post a marker of progress. But imagine that the bridge collapses completely, folding until the beginning and end touch. For you, there are no steps to take, no middle to cross. You're at the start and the finish in one moment. For light, space behaves this way. The beginning of the journey and its end collapse together, erasing the sense of travel. This is why physicists sometimes say photons experience zero time. A photon leaving a star and a photon striking your eye are not separated by an ocean of seconds for the photon itself. It is not a long trek, but a single instant, like the two sides of folded paper pressed together. Let's soften this with another anchor. Imagine writing a postcard to a friend across the ocean. You expect it will take weeks to arrive, sailing by ship or flying by plane. But for the postcard itself, those weeks do not exist. It was placed in the box and it's in your friend's hands with nothing in between. The in-between is only for us, the observers who measure the journey. The photon is like that postcard, skipping the long wait. From our side of reality, of course, the journey is real. The light from the sun takes about 8 minutes to reach us. The light from Andromeda, our nearest large galaxy, takes more than 2 million years. And the faint light from the most distant galaxies has been travelling since the early days of the universe. We live in that distance, in that wait. We measure it with telescopes and calendars. But for the light itself, there is no such duration. Its emission and its arrival are pressed together, like two moments that have always been one. There is a gentle wonder in this thought. When you look at a star, you are seeing light that left long ago, sometimes before humans even walked the earth. Yet that same light has never aged. It is as fresh now as the instant it left, untouched by the billions of years we assign to it. It is both ancient and immediate, old in our counting, new in its own timeless frame. This idea also explains why the speed of light acts as the universe's ultimate limit. For anything with mass, to move at light speed would mean collapsing the very fabric of space and time it travels through. Distance would vanish, time would halt, cause and effect would unravel. The universe does not permit it, except for those things born without mass. Only photons and a few other massless entities are allowed to live at this edge. Let's pause with a dreamlike image. Imagine standing in a field at night. Above you, the stars sparkle. You stretch out your hand and the starlight touches your skin. That light may have crossed unimaginable gulfs, spiraling galaxies, cosmic voids, but for the photon itself, the touch was immediate. It is as if the universe was stitched together by countless threads of light, each one connecting distant points without delay. The cosmos is not just vast, but also intimately woven, bound by the timeless presence of photons. You might ask, does this mean light does not travel at all? In one sense, yes. To us, it moves with a steady, finite speed, and that speed shapes our universe. But in its own timeless existence, there is no sense of progress. It simply is, a link between source and destination. Like two friends exchanging a glance across a room, instantaneous, direct, without need for words, the photon bridges the gap without living in the middle. This can feel unsettling. How can something both take billions of years to reach us and yet not age along the way? The answer is that time itself depends on the frame of reference. For us, those years pass. For the photon, there are no years. Both views are true, because in relativity, truth depends on perspective. Think of two musicians playing different parts of the same song. One hears the melody rising, the other hears the harmony flowing alongside. Neither is wrong. Both are true, yet distinct. In the same way, we measure light's journey as long and slow, while light itself carries no such measure. Two perspectives, one song. There is also a quiet comfort in this. The light from people, places and stars long gone still reaches us, untouched by the passage of their years. It arrives with the same freshness it had when it left, carrying with it a whisper of the past preserved in timelessness. As we drift further into the story, let's hold this thought. For photons, time and distance collapse. They exist in a world where there is no waiting, no growing old, no separation of beginning and end. It is a world alien to us, yet also intimately familiar. For every glimmer we see, every colour we perceive, is built upon this timeless exchange. Our next step will be to imagine what it would mean if time itself froze, not just for light, but for us. Could we ever step into that frozen state? What would it feel like if seconds stopped and the flow of moments ceased? Let us dare to picture that impossible thought as we continue. The trail of our journey now carries us toward the most delicate thought of all. What would it mean if time itself froze? We have followed speed as it stretched seconds, leaned close to light where time slips away, and glimpsed photons that live in a world without waiting. Now, softly, let us dare to imagine what it would feel like if we could step into that state ourselves, into a moment where the seconds no longer move. Begin with a simple picture. Imagine holding an ice cube in your hand. You toss it gently into the air, and just as it arcs upward, it freezes. Not in the sense of becoming cold, but in the sense of becoming still. Suspended. In mid-air, the cube no longer falls, no longer turns, no longer melts. It simply is, caught in an eternal now. This is the image we might use for frozen time, not a broken clock, not a shattered law, but a stillness where before and after no longer exist. Physics tells us that as you approach the speed of light, time stretches towards such a stillness. The Lorentz factor, that steep curve we translated into honey and rubber bands, rises higher and higher, meaning the faster you move, the slower your seconds flow. At the unreachable limit, those seconds would stop entirely. For a traveller at light speed, time would not flow forward. The seconds would no longer tick. Life, as we understand it, could not unfold. Let's anchor this with something more personal. Imagine reading a book. Page by page, the story unfolds, characters change, the plot moves forward. Now imagine the book closed, the covers pressed together. For you, the reader, there is no story. The beginning and the end are pressed into one. The in-between has vanished. If we rode a photon, if somehow we could exist at light speed, our story would be like that closed book. No chapters, no unfolding, no flow of time. But here lies the paradox. You and I are creatures of time. Every thought, every feeling, every memory is stitched into the rhythm of seconds passing. Without time, there is no heartbeat, no breath, no awareness. To imagine living in frozen time is to imagine existing without change, without motion, without experience. It is like imagining sight without light, or sound without air. The thought is haunting, beautiful, but empty of the warmth of living. Still, it is worth lingering here for a moment. If time froze, there would be no aging. A traveller who somehow reached light speed would never grow old, never see their watch tick forward, never feel a day pass. They would be timeless, untouched by decay. But they would also be unable to live a moment longer, for longer itself would have no meaning. We can soften this with a dreamlike metaphor. Imagine a photograph. It captures a moment, preserves it forever. The child's smile, the glint of sunlight, the shape of a hand, frozen. Looking at it, you feel the warmth of that instant, but the photograph itself does not breathe. It holds the now without the flow. Riding a photon would be like becoming the photograph itself, eternal, but without the unfolding life that makes a moment precious. This is why physicists say time freezes only at light speed. It is not that a clock would stop while you still lived your life inside it. It is that the very idea of living, of passing through seconds, disappears. The photon exists outside of our rhythm. It does not wait. It does not grow older. It is always in the instant of its creation and its arrival, with nothing between. There is a quiet lesson hidden here. We sometimes wish time would slow down, that a precious moment could last forever. But to last forever in the frozen sense would also mean to lose the flow, the laughter that comes after the smile, the story that comes after the chapter. What makes time precious is not its freezing, but its passing. A child's smile matters because it vanishes into a laugh, into a memory, into a life that moves forward. And yet, the idea of frozen time is not useless. It reminds us of the contrast, the difference between our world of seconds and the timeless world of blight. Without that contrast, we might never notice the beauty of the passing moment. Just as shadows remind us of sunlight, the thought of frozen time deepens our gratitude for flowing time. So, what would it mean to ride a photon? To step into that frozen realm? In truth, it is impossible. Our bodies have mass. Our lives depend on the rhythm of seconds. To reach light speed would require infinite energy and, more than that, a surrender of the very structure of our existence. We cannot ride that beam. And perhaps that is for the best, for without time there would be no music, no story, no life, only the frozen photograph of a single, eternal now. Still, we can imagine it gently, like a dream before sleep. The thought experiment is enough. Picture yourself stepping into light, and in that instant every star in the sky touches you, every distance collapses, every tomorrow and yesterday vanish. It is not a place you can live, but it is a place you can imagine, and in that imagining lies wonder. As we drift further into the story, we will take this impossible vision as our springboard. What if, even though we cannot reach light speed, we could imagine what it might mean? What if we dared to ask, could such frozen time be harnessed, travelled, used to leap across the stars? The next path in our journey will let us explore what it would mean if we could go light speed, and the paradoxes, the marvels, and the questions that would follow. In the next step of our journey, let us return to a single question posed by a young man in a quiet patent office more than a century ago. His name, of course, was Albert Einstein, though at the time he was not yet the Einstein the world would come to know. He was simply a clerk, filing papers, stamping patents, and letting his mind wander. One day, as the story goes, he asked himself, what would it be like if I could chase after a beam of light? It is such a simple, childlike thought. You can almost imagine him gazing out the window, watching sunlight fall across the street, and wondering, what if I could catch it? What if I ran alongside the beam until I matched its pace? Would the wave of light look still, frozen in mid-air? Would it hover, unmoving, like a ripple on a pond that refuses to spread? At first glance, that seems like a natural answer. If you could match the speed of sound, you might imagine sitting in the middle of a sound wave, hearing it hold steady like a frozen tone. If you could keep up with a racing horse, you could imagine seeing its legs pause mid-stride. But light is different. Light never slows down, never pauses, never lets anyone catch up. Einstein's daydream revealed something profound. There is no such thing as riding the beam. Light is always ahead, always out of reach. Let's soften this thought with a familiar image. Imagine chasing your own shadow. You run faster and faster, your footsteps pounding, your breath rising. Yet no matter how you push, the shadow always stays just ahead, never letting you close the gap. You cannot step into it, cannot stand where it stands. Light is like that shadow, untouchable, always one step beyond. Einstein realized that if he could somehow keep pace with a light wave, he would see something impossible, a frozen ripple, a still vibration. But nature never shows us frozen ripples of light. There is no such thing. The very laws of physics would collapse if such a thing could exist. And so he asked, how can this be? If the speed of light is always the same, no matter how you move, then the world itself must bend in other ways. And bend it does. Instead of letting you catch the beam, the universe stretches your time and contracts your space. It ensures that the speed of light is always the same, whether you are racing toward it or fleeing from it. The result is the beautiful symmetry of relativity. No matter how you move, light always passes you at the same pace. It is the cosmic drummer keeping time for the entire universe, steady and unchanging. Imagine again the daydream. You are Einstein, a young man with messy hair and endless curiosity, picturing yourself chasing a golden beam of sunlight across the rooftops. You push harder, but the beam never pauses. Instead, the world around you begins to change. Your clock ticks slower, the rooftops shorten, the seconds stretch like honey being pulled. Light does not freeze for you. You begin to freeze for light. This thought experiment was the seed of special relativity, a theory that has been tested and confirmed countless times since. But at its heart, it began with a childlike picture of chasing light. And in that picture lies a truth that is both humbling and comforting. The speed of light is not just a number, it is the structure of reality itself. Let's bring this closer to everyday life. When you walk down the street and see your shadow stretching ahead in the setting sun, remember that you are living Einstein's thought experiment. You cannot catch that shadow, just as you cannot catch light. The rules of the universe prevent it, not because of cruelty, but because of balance. If you could catch it, if light could freeze, then time itself would unravel. There is also a quiet poetry in the fact that this great theory, the one that changed everything about how we see the cosmos, was born not from a laboratory, but from a daydream. It was not hammered out in chalk dust, but whispered in the imagination of a curious mind. Einstein's beam of light was not only physics, it was wonder itself. If we dare to continue the thought to imagine riding a beam of light, we can picture ourselves dissolving into that timelessness we have spoken of. We would see no ticking clocks, no passing moments. The universe would rush by in a blur, every star's distance compressed, every second erased. The ride would be not a journey, but a collapse of all journeys into one single, eternal now. But of course, this is not a ride we can take. The laws of physics hold us back gently but firmly. We are creatures of mass, of heartbeats, of seconds flowing. To us, chasing light is like chasing our shadow, beautiful to imagine, impossible to achieve. Still, there is meaning in the imagining, for by picturing what cannot be, we come to understand what is. By chasing a beam of light in our minds, we learn why time slows, why space contracts, why light is the universal speed limit. We see that the impossibility of catching it is not a barrier against us, but a truth that holds the universe together. So let us keep the picture in our minds. A young clerk in a quiet office, gazing out the window, lost in a daydream. His thought gave birth to relativity, to the idea that time and space are not rigid, but soft and flexible, shaped by motion and light. And it all began with the impossible image of riding the beam. As we drift further into the story, the next step asks an even deeper question. If we could somehow reach that speed ourselves, if we could ride the beam in reality, what would it mean? What would life be like in a world where time never moved, where heartbeats never followed one another, where a second never ticked forward. That is the haunting possibility we will now imagine, the idea of a timeless journey. As we drift further into the story, let us take one more step into imagination. We have pictured chasing the beam, always just behind it. But now, softly, let us imagine something even more impossible. What if we truly could ride alongside light itself? What if a human being, bound by mass and heartbeat, somehow touched that frozen edge where time no longer flows? To begin, picture yourself climbing aboard a spacecraft that has been built to achieve the impossible. Its hull gleams, its engines hum with endless power. You take your seat, and as it accelerates closer and closer to light speed, you feel nothing unusual. Inside, your heart beats, your breath flows, your mind wanders just as it does now, but outside the universe is shifting. Seconds are stretching, distances are shrinking, and reality itself is bending around your motion. Finally, you reach the limit, light speed itself, and then everything stops. Not the ship, not the stars, but time itself. No heartbeat follows another. No breath flows in or out. Your clock does not tick forward. In fact, forward no longer exists. The entire rhythm of your life, every second that once carried you onward, is gone. For you, there is no tomorrow, no yesterday, no next. There is only the frozen instant of now. We can soften this with a metaphor. Imagine a book. When open, each page flows into the next, the story unfolding with characters and events. But now, imagine closing the book. The cover touches, and the story within no longer moves. The beginning and the end are pressed together, and the middle has vanished. Riding at light speed would be like becoming that closed book. Your story held in place, but never allowed to unfold. This raises a haunting but gentle question. Could existence even make sense without time? To exist, as we know it, is to change. To feel a thought come and go, to hear one note after another, to remember a moment and then live the next. Without the flow of time, there is no awareness, no heartbeat, no memory. There is only a stillness that may as well be emptiness. Think of a photograph. It captures a moment forever. The smile, the sunlight, the movement of a hand, preserved in perfection. But a photograph does not breathe. It does not continue. It is a frozen now, a single instant torn away from the river of time. A traveller at light speed would be like the photograph itself, eternal, untouchable, but silent, without the rhythm of life. This is why the thought experiment, though beautiful, is also impossible for us. We are creatures of mass. Our bodies require seconds to tick, breaths to follow one another, hearts to beat in rhythm. Without time, we are not ourselves. We are only frozen images of who we once were. To live at light speed would not be to live forever, but to stop living altogether. And yet, there is a strange comfort in imagining it. For in picturing the timeless journey, we see the value of the flow we do have. We realize that it is the very passing of seconds that allows us to love, to grow, to change. A child laughs and then grows taller. A loaf of bread rises, bakes, and is shared. A sunset slips beneath the horizon, giving way to stars. These things matter because they pass. If they froze, they would lose their meaning. Let's soften this further with another anchor. Imagine music. Each note matters not because it is eternal, but because it is followed by the next. A song frozen on a single note would not be music at all. It is the sequence, the rhythm, the rise and fall that make the song beautiful. Our lives are the same. They are songs carried by time, and without the flow, the melody vanishes. So if we could ride the beam, we would not find immortality. We would find silence. No heartbeat, no breath, no song. Only the eternal instant, It is not a place for us to go, but it is a place for us to imagine, to understand why our flowing seconds are precious. And in that imagining, we glimpse a deeper truth. Time is not a curse, but a gift. It gives us stories instead of snapshots, music instead of frozen notes. It lets us move through seasons, through growth, through change. To freeze it would be to end it. To let it flow is to live. Perhaps this is what Einstein himself realized when he thought of chasing light. The impossibility of riding the beam was not a disappointment, but a revelation. The very fact that we cannot join light in timelessness is what allows us to exist at all. We are not meant to be photons. We are meant to be travelers carried gently forward, second by second, in a universe that bends but does not break. As we let this thought settle, the next path before us grows darker, stranger. For what if, in trying to imagine timelessness, we stumble into paradox? What if frozen time creates contradictions, messages arriving before they are sent, causes unravelling from effects? Our quiet exploration now turns to these limits, the paradoxes that wait when we try to push relativity too far. From here, the story opens into a twilight place, a boundary where imagination begins to stumble and contradictions appear. We have followed speed to the edge of light, peered into timelessness, and dared to imagine what riding a photon might mean. But as soon as we try to step beyond, into a world where time might freeze or even run backward, paradoxes begin to whisper at us. One of the most haunting is the breakdown of cause and effect. In our ordinary lives, the arrow of time is simple. You drop a cup, it shatters. You light a match, it burns. You speak a word, and then it is heard. Causes lead to effects, one step after another, like footprints in a row across sand. But if we imagine moving faster than light, or living at light speed ourselves, this order begins to twist. Suddenly the footprints cross over one another, some leading backward, some appearing before they were made. Let's anchor this in something familiar. Imagine sending a letter to a friend. Normally, you write it, place it in the box, and only later does your friend read it. Cause, then effect. But what if your friend opened the mailbox and found your letter before you even wrote it? That is the kind of paradox faster-than-light communication would create. Events would lose their order. Effects might appear before their causes. The universe would become tangled in contradictions. Physics gives us gentle warnings about this. The constancy of the speed of light is not only a speed limit, but also a safeguard for causality. It ensures that no message can outrun the sequence of time, that every event has its place. Remove that safeguard and the careful logic of the cosmos begins to unravel. This is why many physicists suspect the energy barrier we described earlier, the infinite effort required to reach light speed, is not just an inconvenience but a necessary wall. It prevents us from stumbling into paradox. The wall protects the story of time from being torn apart. Let's picture this with an everyday metaphor. Imagine a library with 1,000,000 books. Each one must be read in order, page by page, so the story makes sense. If you shuffle the pages, pulling the ending to the front, mixing paragraphs at random, the story collapses into nonsense. Faster than light travel or communication is like tearing up the library, scattering its pages. The universe itself would lose coherence. And yet, we humans are drawn to paradox. Our minds love to wander into the what if. What if we could send a signal to the past? What if an astronaut could arrive home before they left? These thoughts appear in stories, in films, in dreams. They are unsettling, but also fascinating. They remind us of the fragility of our ordinary experience of time. There is another layer to this as well: communication. Imagine two people trying to talk across a distance. If one could send a message faster than light, the other might receive it in their own past. To one, the conversation would flow forward. To the other, it would flow backward. The dialogue would lose all meaning, looping into contradictions. It would be like trying to play a duet where one instrument plays the notes in reverse. The music collapses, and so we see that light speed is not just about how fast we can move, it is about protecting the harmony of time itself. The limit is a way of keeping the universe coherent, of ensuring that causes remain before effects, that stories can unfold with order, that songs can be sung in sequence. Without the limit, paradoxes would creep in and the melody of existence would falter. Let's rest with a softer metaphor. Imagine a loom, weaving threads into fabric. Each thread must cross in order, one after the other, to make a pattern. If you pull threads out of sequence, the pattern dissolves into chaos. The speed of light is like the tension of the loom. It holds the thread steady so the fabric of space-time can exist. For us, the paradoxes serve as gentle reminders of our place. We are creatures bound to time's arrow. We live within the order of cause and effect, where seeds grow into trees, where rivers flow downhill, where tomorrow comes after today. The fact that we cannot break this order is not a loss but a gift. It allows us to trust in the story of life, to live without contradictions tearing our reality apart. Still, it is worthwhile to imagine the edge, even if only in thought. By playing with paradox, we learn why the limits exist. We see that the wall at light speed is not there to frustrate us, but to protect the coherence of the universe. It is a reminder that reality is both flexible and firm. Time stretches and bends but never breaks. As we drift further along, the path now carries us into even stranger territory. If paradox lies beyond light speed, then what about the purely speculative? Physicists have written about hypothetical particles that would always move faster than light. Imaginary sprinters called tachyons. They are not proven, and perhaps they never will be, but they offer a playground for our imagination. Could such beings exist? And if they did, what would their timeless journey look like? That is the question we will gently explore next. The trail of clues now leads us into the land of speculation, a quiet meadow where imagination wanders freely. Here we meet creatures that may not exist at all, but that nonetheless haunt the equations of physics, tachyons. The word itself comes from the Greek tachys, meaning swift. Tachyons are imagined as particles that would always move faster than light, not sometimes, not briefly, but always. Unlike us struggling to approach the cosmic speed limit, tachyons would be born beyond it, forever outpacing even the fastest photons. At first glance, the idea is playful. What would it be like to exist always faster than light? To be the ultimate sprinter of the universe, racing so far ahead that even starlight cannot keep up. But then the paradoxes return, whispering again. For if something can move faster than light, it can send ripples backward through time, and once again, cause and effect become tangled. Let's soften this with an anchor. Imagine waking up tomorrow and finding today's newspaper already on your doorstep. You flip through the pages and see events described that you have not yet lived. That is the kind of mischief tachyons would allow. Glimpses of effects before their causes, stories before their beginnings. Physicists introduced tachyons not because they had been seen, but because certain mathematical solutions seemed to suggest them. In the equations of relativity and quantum fields, sometimes strange possibilities appear, like phantom paths in the forest. Tachyons are one such phantom. No detector has ever found them. No experiment has confirmed them. But their shadow lingers in theoretical discussions, a reminder of what might happen if the cosmic limit were not absolute. There is, however, a peculiar twist. If tachyons were real, they could never slow down to light speed, just as we can never speed up to it. For them, the boundary of light speed would be unreachable from the other side. To us, light speed is the summit of the mountain. For them, it would be the floor of the valley, a place they could never climb down to. They would always remain beyond, forever out of reach. This balance is curious and almost poetic. We, with mass, can never touch the light. They, if they existed, could never fall back to it. The barrier is a two-way wall keeping us apart. We live below, bound to time. They would live above, in a realm where time itself might flow strangely, perhaps even backward. But before this becomes too unsettling, let's step back and smile at the wonder of it. Tachyons have never been observed, and many physicists suspect they never will be. They may exist only in imagination, like mythical creatures painted in the margins of maps. Still, they serve a purpose. By picturing them, we glimpse why the speed of light matters, why its boundary protects the logic of the universe. Tachyons are the what-ifs scribbled in the margin, the reminder of the chaos that would arise if the limit could be broken. Let's anchor this in something softer. Imagine a racetrack where some runners always sprint slower than a certain pace, and others always sprint faster, never meeting in the middle. We are the slow runners, bound below light speed. Photons rest at the dividing line, never wavering. Tachyons, if they existed, would always be far ahead, unseen, their race invisible. The track is shared, but the lanes never cross. Another way to picture it is with a river. We drift with the current downstream, each second carrying us forward. Light rushes along the very edge of that flow, never falling behind. But tachyons, if real, would already be beyond the river's edge, moving in ways we cannot imagine, perhaps even drifting upstream against the current of time. We cannot reach them, they cannot return to us. For bedtime, perhaps the gentlest lesson here is not about tachyons themselves, but about the beauty of speculation. Science is not only about what has been measured and proven, it is also about what can be imagined, tested in thought, and then weighed against reality. Tachyons remind us that imagination is part of discovery. Even if they remain forever mythical, they have guided us to ask deeper questions about speed, causality, and the limits of the possible. So while you are unlikely to ever hear the click of a tachyon in a detector, you can still dream of them. Imagine them as playful spirits of the cosmos, forever outrunning even light, forever carrying tomorrow into today. They may never exist, but their story helps us appreciate why we remain bound to our slower lane, protected from paradox by the cosmic speed limit. As we drift further into the story, we leave behind these phantom sprinters and turn to another dream. If tachyons are speculation, perhaps there are other ways to leap beyond the ordinary. Wormholes and warp bubbles, mathematical doorways through space-time, have captured the imagination of physicists and storytellers alike. Could we fold the universe so two distant points touch? Could we ride a bubble of space faster than light itself? Let us step gently into that dream next. From here, the story opens into another meadow of speculation, one filled with bridges and bubbles, with shortcuts written into the very fabric of the cosmos. If tachyons are the phantom sprinters who forever remain out of reach, then wormholes and warp drives are the whispered doorways, not faster than light by breaking the rules, but by gently sidestepping them. Let's begin with wormholes. Imagine taking a sheet of paper. Place two dots far apart on its surface, each representing a distant star. If you measure across the page, the distance seems long and unyielding. Now fold the paper so the two dots touch. Suddenly, the long journey collapses into a single step. That is the essence of a wormhole, a tunnel through space-time connecting two distant points directly. The idea arises naturally from Einstein's equations of relativity, the same mathematics that showed us time dilation and black holes. Hidden within those equations are solutions that look like bridges, sometimes called Einstein-Rosen bridges. They suggest that space-time could, at least in theory, bend back on itself, creating a tunnel between faraway regions. But as with all beautiful ideas, reality complicates the dream. A wormhole, if it existed, would be unstable, collapsing before anything could cross. To hold it open, physicists say, would require exotic matter, stuff with negative energy, unlike anything we have ever found. Without it, the tunnel slams shut before you can take a single step inside. Still, the image lingers, a tunnel through the universe, a hidden doorway where distance collapses. It has inspired countless stories, from science fiction to bedtime wanderings. Even if wormholes remain imaginary, they remind us of the flexibility of space-time, of the strange possibilities that emerge when we bend our thinking as much as the cosmos bends itself. Now let us turn to warp bubbles. This idea comes from a thought experiment by physicist Miguel Alcubierre in the 1990s. He asked, what if, instead of pushing a ship through space, we stretched space itself? Imagine placing a ship inside a bubble. The space in front of the bubble contracts, the space behind it expands, and the bubble is carried forward. To an outside observer, the bubble could appear to move faster than light, though the ship inside never breaks the local speed limit. The everyday anchor here is simple. Think of a moving walkway at an airport. You stand still, but the walkway carries you forward. To people watching, you glide along at surprising speed. A warp bubble is like the ultimate moving walkway, not built of rubber and steel, but of space-time itself. But again, the dream meets the wall of reality. To create such a bubble would require enormous amounts of energy, so vast that it may be forever beyond our reach. Worse still, it too would require exotic matter, with properties we've never seen. For now, warp bubbles remain an elegant sketch in the mathematics of relativity, beautiful on paper, but fragile against the weight of physics. And yet, there is something deeply comforting in these ideas. Wormholes and warp drives may never be built, but they remind us of the creativity of the universe. They tell us that space and time are not rigid backdrops, but flexible fabrics, capable of folding and stretching in ways we barely understand. Let's pause with a dreamlike image. Picture the night sky as a vast quilt stitched with stars. Normally, you must walk its length one patch at a time. But if you fold the quilt so two stars touch, you can leap across in a heartbeat. That is the poetry of wormholes. And picture then a bubble drifting across the quilt, carrying you forward without effort, the stars sliding past as if you were standing still. That is the poetry of warp drives. Even if these things remain only in equations, their presence in our imagination matters. They stretch our thinking, showing us that physics is not only about limits, but also about possibilities. Einstein himself often said that imagination is as important as knowledge. For knowledge tells us what is, but imagination tells us what could be. So when you read about wormholes in a novel, or hear about warp drives in a film, remember that behind the fiction lies real physics, real equations, real speculation. It may never leave the page, but it whispers that the universe is more malleable than it appears. And perhaps in a quiet way, these dreams already enrich our lives. For when we look at the night sky, we cannot help but imagine what it would be like to fold space, to bubble through the stars, to skip across light years in a single breath. These dreams comfort us, reminding us that we are not bound only to what we can see, but to what we can imagine. As we drift further along the trail, we must return gently from speculation to reflection. Wormholes and warp bubbles may remain dreams, but the very fact that the equations allow them tells us something profound. That time and space have boundaries, but also possibilities we do not yet grasp. In our next step, we will ask what these boundaries truly mean. What is the ultimate rulebook of the cosmos? Is time something to freeze, or is it a fabric that insists on flowing, bending, but never breaking? The trail now carries us toward those ultimate boundaries, where physics meets philosophy once again. The trail of clues leads us now to the edge of the map, the ultimate boundaries of what the universe seems willing to allow. We have seen how time bends under speed, how it slows under gravity, how photons live in a realm without seconds, and how imagination has built wormholes and warp bubbles as possible escapes. But even with all these wonders, the universe whispers the same truth. There are boundaries, and those boundaries are as much gifts as they are walls. Think first of the speed of light. It is not merely a number, not simply 300,000 kilometers each second, though that is the way textbooks often present it. It is the pace at which causality itself is safeguarded. It is the maximum rate at which information, influence, and connection can move. If this boundary did not exist, messages could arrive before they were sent, causes could follow effects, and the fabric of reality would unravel. We can anchor this in something simple. Imagine a playground slide. You can climb up the ladder, you can rest on the platform, you can slide down again, but no matter what, gravity pulls you in one direction. The slide may be long or short, steep or gentle, but you cannot slide upward on your own. The rules are firm, and those rules preserve the fun of the game. The speed of light is like that gravity. It ensures that time has a direction, that events remain ordered, that the cosmic game makes sense. This limit, though frustrating to dreamers of faster-than-light ships, is part of what makes our universe coherent. It is a boundary written into the geometry of space-time. In Einstein's equations, the speed of light is not just a speed, it is the slope of the fabric itself, the line that tells us how space and time are woven together. Beyond that, we find gravity's role. The deeper the well of gravity, the slower time flows. At the edge of a black hole, time nearly halts compared to the outside world. But even there, the rules remain. Time bends but never breaks. The event horizon is a kind of boundary too, not just for light, but for causality. Cross it, and the story becomes cut off from the rest of the universe. These boundaries are not optional. They're written into the very definition of reality. And then there are the dreams, tachyons always racing ahead, wormholes folding space, warp bubbles carrying ships faster than light. They remind us that imagination is vast, but they also remind us that reality is selective. The mathematics may hint at shortcuts, but the physics demands a price we cannot pay. Exotic matter we cannot create, energies we cannot harness, paradoxes we cannot allow. These dreams may remain forever in the realm of what if. Yet there is no disappointment in this, for the limits themselves are what make life possible. If photons experienced time, they would decay, age, lose coherence. If there were no speed limit, the order of events would dissolve, and the story of the universe would collapse into nonsense. If wormholes opened casually, the stability of space itself would unravel. The boundaries are not failures. They are the frame of the painting, the edges that let the picture exist. Let's soften this with an everyday anchor. Imagine baking bread. The dough rises, expands, fills with air. But it is the crust, the outer limit, that gives the bread its form. Without the crust, it would simply spill outward endlessly, formless, unsatisfying. In the same way, the boundaries of light speed, of gravity, of causality, give the universe its structure. They are the crust around the dough of existence. Or think of a river. It is the banks that keep it flowing. Without them, the water would spread thin and vanish. The speed of light, the arrow of time, the boundaries of space-time, these are the banks of the cosmic river. They do not constrain the water, they allow it to exist as a river at all. It may seem strange, then, to ask whether time could freeze. We have chased the thought all the way to light speed and beyond, and the answer the universe gives is gentle but firm. Time can stretch, slow, bend, approach stillness. But to freeze entirely is not for us, not for matter, not for life. That state belongs only to photons, those massless messengers who know no seconds. For us, time must flow, because without it there is no life, no thought, no music, no story. And yet, in imagining the impossible, we come to appreciate the possible. We see that our flowing seconds are precious. that their very fragility gives them beauty. To wonder if time could freeze is to remind ourselves why its flow matters. Like asking if a song could last forever, we realize that its ending is part of its meaning. So here, at the universe's boundaries, we arrive at a gentle reflection. The rules may seem stern, but they are also kind. They prevent paradox, preserve order, and give us the gift of an unfolding world. Time may not freeze, but it bends in ways that inspire awe. The speed of light may be unreachable, but it lights our path across the cosmos. Gravity may slow our seconds, but it also cradles us on Earth, keeping our feet to the ground. As we drift further into the story, we now leave speculation behind and return to ourselves. The next path carries us toward gratitude, for the one-way flow of time, for the arrow that carries us forward, for the moments that matter because they pass. We will pause to reflect on living within time, on finding comfort not in breaking its rules, but in cherishing them. Our quiet journey now carries us back from the edges of physics into the warmth of everyday life. We have wandered through cosmic limits, timeless photons, and impossible dreams of riding the beam. But as we pause here, we realize something important. We're not meant to live outside of time. We're meant to live within it. And that is not a loss, it is a gift. Think for a moment of bread rising in an oven. You mix the ingredients, knead the dough, leave it to rest. Slowly, over minutes and hours, it swells, softens, and fills with warmth. If time were frozen, the bread would never rise. If it leapt instantly from dough to loaf, it would lose the gentle alchemy that makes it nourishing. It is the flow of time, the patience, the waiting, that turns flour and water into something more. Or consider a sunset. The sky does not shift all at once. It glows slowly, fading from gold to amber to deep violet. Each colour lingers, then yields to the next. If the sunset froze, if it were only one eternal shade, it would lose its beauty. The passing of each moment is what makes the whole spectacle breathtaking. This is how time blesses us, by passing. The very thing that sometimes frustrates us, seconds slipping away, hours vanishing too quickly, is also what gives our lives meaning. If everything lasted forever, if moments froze, we would lose the gentle progression that makes those moments precious. Children remind us of this most vividly. You watch them grow, tiny hands learning to grasp, first steps on unsteady legs, first words spoken in quiet wonder. Each stage passes, and part of you may wish it could last longer. But it is precisely because it does not last that it holds such tenderness. Childhood becomes memory, and memory becomes part of the story of a life. In this way, the arrow of time, always pointing forward, is not a curse. It is the thread that stitches our days into a tapestry. It carries us from seed to tree, from laughter to silence, from beginnings to endings. The speed of light may keep us from stepping outside of this flow, but perhaps we were never meant to. Perhaps the gift is not timelessness, but time itself. Let's pause with another image. Imagine listening to a piece of music. Each note matters because it is followed by the next. If the song froze on a single tone, even a beautiful one, it would no longer be music. It is the sequence, the unfolding, that creates melody. Our lives are the same. They are music played by time, and the beauty lies not in one note lasting forever, but in the notes rising and falling together. We sometimes long for more time, or wish time would slow. And yes, the thought of frozen time carries a strange allure, but when we look closely, we see that it is the impermanence of moments that gives them their glow. A meal tastes sweeter because it ends. A night feels softer because it yields to morning. A life feels meaningful because it cannot be repeated. Einstein himself, who gave us the equations that reshaped our view of time, once wrote in a letter that past, present and future are only illusions, even if stubborn ones. To him, the universe was like a great block, with all events woven together. And yet, he still lived, loved, and mourned within the arrow of time. Even the man who showed us that time is relative still found comfort in the flow of his own days. So, as we settle here in reflection, let us be grateful for our place within time, grateful that bread rises slowly, that sunsets fade gently, that children grow, that music unfolds, grateful that we are carried forward, second by second, not into frozen timelessness, but into the richness of life. Think of your own life, softly, the laughter you've shared, the moments that surprised you, the quiet mornings, the restless nights. All of these exist because time flows. They could not exist in a frozen world. They are gifts, given only once, yet given fully. And maybe this is why we dream of time freezing, because it reminds us of how much we cherish what we already have. We do not truly want frozen time. We want more of it, or we want to hold on to what passes. But the passing is what makes it real. As our journey draws toward its close, let us carry this thought. Time's limits are not walls to resent, but boundaries that shape meaning. Like the banks of a river, they guide the flow. Like the crust of bread, they give form. Like the rhythm of music, they create beauty. The next and final step of our exploration will bring all of this together. We will revisit photons and paradoxes, frozen time and flowing days, and let it all settle into one soft farewell. The mysteries of light speed may remain unsolved, but we can rest in the gentle truth that time, as it flows for us, is enough. And so, we arrive at the final stretch of our journey together. We have wandered through time as it bends and slows, through photons that never age, through imagined particles and folded maps of space. We have asked whether time could ever freeze, and we have discovered that while it can stretch, slow, and nearly halt, it never quite stops for us. Time is the rhythm of our lives, the current that carries us forward. Tonight, as you rest, you have followed light across the cosmos. You have stood beside twins who age differently, listened to muons falling from the sky, and smiled at satellites that keep our pizza deliveries punctual. You have imagined running through honey as seconds stretched, folding space like paper, and gazing into the stillness of photons that never live in before or after. These stories, though cosmic in scale, are held together by the same gentle truth. Time flows differently depending on where you are, how you move, and what gravity you stand within. But in every case, whether slowed by speed, stretched by gravity, or erased for light itself, time never abandons its role. It gives order to the universe, keeps cause before effect, and lets the story unfold. The limits we found, at light speed, at black hole horizons, in the dreams of wormholes, were not barriers meant to frustrate us. They were the frame of the painting, the banks of the river, the crust of the bread. Without them, there would be no song, no story, no river at all. Perhaps this is the deepest gift science gives us. Not just facts about particles and clocks, but a way to see the wonder in the ordinary flow of seconds. Relativity shows us that time is elastic, personal and strange, yet lived time, the seconds in your heartbeat, the minutes of a conversation, the hours of a night like this one, is what makes us human. It is what lets us grow, love, remember, and dream. So, as we settle into stillness, let's recall the images that guided us. The swing bound by its chains, never rising past its limit. The accordion squeezed shorter as speed grows. The muon candle that burns longer because its seconds stretch. The postcard that skips the wait. Like a photon born and absorbed in the same instant. The folded map that lets two cities touch. The playground slide, always pulling us forward. Each of these was a window into the strange nature of time, but also into the beauty of our own fleeting moments. If you close your eyes now, you may imagine chasing a shadow in the fading light, never quite catching it, yet smiling at the chase. That is what Einstein did in his mind, and from that childlike daydream, he gave us relativity. It is a reminder that even the deepest physics can begin with a playful question whispered to oneself. And maybe tonight, you too carry a question into your dreams. Could time freeze? Could we ever ride the beam? The answer softly is no, not for us. But the asking itself is what matters, for in wondering we see more clearly what time gives us, not an endless stillness, but a flowing song. Like all songs, it has a beginning, a middle, and an end, and that is what makes it beautiful. Each note gives way to the next, each day yields to another, each life unfolds in sequence. We cannot stretch our seconds to infinity, but we can cherish them as they pass, knowing that their very passing is what makes them precious. So let this be our soft farewell. The mysteries of time will always remain partly hidden, folded in the fabric of the cosmos, but here, in this quiet moment, we have touched them gently. We have seen how seconds stretch, how light lives without them, how limits protect the story from unravelling. And we have returned to the comfort that time, in its ordinary flow, is exactly what allows us to live, to laugh, to love, and to rest. Whether your eyes are still open, gazing at the glow of a screen, or already drifting closed, heavy with sleep, may this journey leave you calmer, quieter, more at ease with the rhythm of your own life. Time may not freeze, but it holds you softly, carrying you forward in its steady current. And so, as the night deepens, let the flow of seconds lull you into rest. The universe keeps its rhythm. The stars shine their timeless light. And here, in this moment, you are safe within the gentle passage of time. Sleep peacefully, wherever and whenever you may be.